So, has anybody seen the movie Interstellar?
No.
The eyes.
I made a mug cake.
What flavor was it?
Okay.
It was flavored
I'm
chocolate.
confused. Have you seen the movie Interstellar?
No.
Is it good?
Should I?
Telling you I
I
made
feel like I
cake.
should.
Trace, that's wonderful. So nobody's seen the movie Interstellar. Okay.
I've seen the
that's
movie.
fine. This is an image from that, so this is their rendition of what a black hole might look like. We've never actually seen a black hole for a few reasons. Number one, to bounce or to see something, you have to bounce light off of it. Okay? The only way I can see Mateus over there is that light from the lights from the sun bounce off of her, and then that light goes into my eyes, and then my brain makes an image. Same thing with everything. If we take away all of the light, so if we made this room so that no light could get in, if we were emitting no light from the fixtures up there, there's no way I would be able to see her. Yes.
How come cats can see in the dark?
If cats can't see in the dark, they can just see well in very low light. Yeah, so we say they can see in the dark, but they just have a lot more rods in their eyes to pick up lower light. But if you put them in pitch black, you won't be able to see any better than pitch black. Okay? Yes,
Are
Alyssa.
there pigs in there?
Emily.
So are there any animals that can actually see in the dark, or are they all just kind of...
No, there's no animals that can see in the dark. Now there are some animals that have different organs that will let them get senses that. Yes. That it's not the same as seeing, but they can get some information that if their eyes are not able to work out. You've heard the term blind as a bat, I'm sure. Bats actually have pretty good vision. But they also have a way of getting some information about their surroundings through what's called echolocation. So they send out sounds, and then those sounds bounce off things, and the way they come back, they're able to determine where things are. It's not seeing. They don't see using that. It's just a completely different sense. It's no different than saying, I can hear where somebody is. That's not the same as seeing.
How can we only see, like, you don't see the dark again, literally on it?
Well, it's just a behavior.
There's no special reasoning on that one.
No, now, the fact that they're able to use the echolocation probably has been driven by the fact that they are more nocturnal. And not all bats do that. It depends on how they feed. Like, that has to do more with insectivore bats that catch little flying things in the night. Fruit bats, they don't really use echolocation. They don't really feed. Okay. So, you have to bounce light off of something to see it. We see the moon because light bounces off of it. Well, it has to at least, I should back up and say it. We either have to bounce light off of it or it has to emit light. Okay? We see light from the sun because the sun emits that light. We see light from these lights because it emits. But like planets and moons all have to have light that bounces off of it. It's hard to find a black hole because light doesn't bounce out. Light falls in.
Great, thank you.
Okay?
Alright, so if we did get stuck into it, like, I know we would die, but, like, would we be, like gasping for air?
Well, we're going to talk about that. I do want to back up, and we want to stay away from the term sucked into. Okay?
Pulled in.
Yeah, you get pulled in, you fall in.
Or falling.
Well, right, because it's all gravity. The reason why light falls in is because the gravity is so strong. So, when you fall off a ladder, you don't say the earth sucked you down, you say you fell, right?
Yes, I fell on Sunday. I sprinted, and in fact, from
Did you get stuck?
I fell.
And you couldn't get up.
So, the same thing with light. As light goes by a black hole and it gets pulled in, I mean, it's falling in. It's being influenced by gravity, the same as Austin was when he fell off the ladder. Okay?
It was just a lot of
Repeated
Cool.
from
laugh.
the deer.
Repeated laugh. Repeated laugh.
You were my father did. And my Uncle Bill. I was laughing like this.
Okay, we're going to throw out a term here. Make sure that I spell that closely, right? It's called the Schwarzschild radius.
That sounds aggressive. So like Arnold Schwarzenegger's.
Sort of good, but not. Okay? The Schwarzschild radius is the size an object has to be squeezed to become a black hole.
You could never just see a big black hole that pops out on Earth.
Probably
No.
not.
I'd squeeze you.
Yes, Trace. Every object has a Schwarzschild radius, no matter what object it is. If you took me and you squeezed me to a tiny enough volume, then the gravity between all of my parts would be strong enough to pull it into a black hole. A small black
And
hole,
you die.
but I'd become a black hole.
Yeah, and we'd all die if we died because we were falling in and there's no light, so we'd all die.
Yeah, because
Sounded like you were being too out there.
That's a little bit of a misconception we're going to talk about.
What?
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 So, the Earth has a Schwarzschild radius. The size of the Earth's Schwarzschild radius is about the size of this yo-yo or an apple. So if you were somehow able to take the Earth and squeeze it down and push it down so that it only took up the space of an apple, it would become a black hole.
That's so tiny.
That is very tiny. Okay? Now, for most normal objects, the Schwarzschild radius is just too small. Do you have a question, Jacob?
Yes, how big would that black hole be?
It would be the size of the apple.
Okay.
I didn't know the size of the Schwarzschild.
Gross.
It can grow if it gains more mass. You're getting a little bit ahead. Okay? For most objects, planets, and in fact, most stars, the Schwarzschild radius is just too small. In fact, our sun, which of course is much bigger than the Earth, there's not enough gravity there to squeeze it down to its Schwarzschild radius. So our sun just doesn't have enough mass to ever become a black hole. So this thing, I mean, even though all objects theoretically have a Schwarzschild radius, there's just no forces that can get them that small, except for large stars. So large stars have enough mass / gravity to become black holes. And really large, we should put really large. It's only the biggest stars have enough gravity to be able to squeeze the mass down to the point where it will become black. So, remember yesterday how we talked about neutron stars form after a supernova goes off, and the gravity pulls everything down so it squeezes the protons and electrons together to make just a big ball of neutrons. So if an even greater star goes through a supernova explosion, the thing that's left, the gravity will squeeze it down until it goes beyond the Schwarzschild radius and becomes a black hole. Jacob.
If it were possible, what would happen if you touched a black hole?
Okay. Hold on to that thought just a minute. You guys have lots of questions and trying to go through a logical progression here so we can understand how it works. Yes?
How then is the Schwarzschild radius so cool?
It would be very tiny. I mean, the size of like an atom. You wouldn't be able to see.
No, big as
Diamond?
Very small.
Yeah, I'm not touching my pencil because
You're made up of-
touch the phone.
Yeah, you're making up of trillions of atoms. So you have to take all of those atoms and cram them into the space of one.
About the electrons that are in between you and the objects, how does tape stick to it? Is it attracted?
There's a lot of electrodynamics that go on there.
Let's talk about it.
We don't really have time to talk about that. Let's talk about black holes. So it's a good question, but it's already beyond the scope of what we're talking about today. Okay, now, when a black hole is able to form this Schwarzschild radius, right? When we actually have a black hole, that size gives us what's called the event horizon. Okay? Now here's the thing you have to clamp your mind around. Let's say we were able to, just so we have something to focus on, we were able to take the Earth and we were able to somehow squeeze it beyond its Schwarzschild radius. The thing is, once gravity takes over at that point, it doesn't stop at the size of the apple. The gravity pulls everything in farther and farther until it's at an infinite point. So the actual material of the Earth isn't the size of an apple. It keeps going and squeezes even smaller. What's left behind that is the size of the apple is this thing that we call the event horizon. The event horizon is the place where if light goes beyond that, it can't come back up. Okay? So it does look. My marker just fall into the trash. Oh, here it is. Okay, so the event horizon is the area beyond which light can't escape. Okay, so if this is the event horizon of our Earth black hole, if a light wave goes by here, it'll be able to keep going. Now, it will change direction. We'll talk about that in a minute. But if it comes closer than that, if it comes into that area that's taken up by the event horizon, then it gets pulled in and it doesn't come out. Or it can't.
So does that mean the inside of the black hole can get light?
The inside of the black hole is going to collect anything that comes within the event horizon.
So if it collects enough light, will it be light inside?
Well, we don't really know what happens. The thing is, and I'll get to your questions in a minute, but what we want to write down here is, beyond the event horizon, laws of physics break down. And we don't know what will happen. There's no way of knowing, there's no way of ever knowing what actually happens inside of a black hole. We can talk about all the things that will happen up to the event horizon. So that's easy to describe. But beyond the event horizon, I mean, there's just no way to know because the gravity is so extreme. There's no way of anything ever getting out. That includes information getting out. All right, let's start with Matea first.
Okay. So can black holes like eventually not have enough gravity and like just disappear?
Sort of, but not in the way that you're thinking. There is a way that black holes can evaporate. And whether we get that, because that you have to know a little bit about quantum physics. We may try to touch on that if we have some time at the end.
What do you mean by evaporate? They're not even made out of gas. It's not that, it's just gravity.
Well, exactly. And that's the confusing part about it. So I don't know if we want to necessarily try to tackle that today. We'll see. But for the most part, black holes are just kind of where they are. They're not gonna grow any bigger if they're just sitting there. But if they're able to pull more stuff in, that's going to add more mass, and they will get bigger in the event horizon. So black holes will kind of stay where they are for the most part. But if something gets too close to them and gets pulled in, then they'll grow. Okay, David.
So how big would the black hole in the middle of the nucleus, how big would the star have to be?
That likely formed by the more than one star becoming a black hole, and then those black holes merge.
That would be a giant.
Yeah. There's no stars that have ever been that big, so that's a conglomeration of black.
If there was like a green star, would that
We don't really see green stars because of the way the wavelengths of light come out. It kind of skips over the green. You would be scared, yes. Alyssa,
Okay, so how thin are they?
what do you mean how thin?
Like if you're looking at it from a side view.
Oh, okay. So we say black hole, and usually when we think of a hole, we're thinking of like a space in a two-dimensional object. But this isn't space. A black hole is a sphere. Okay, the event horizon itself is a sphere. So if we go back to this, you can maybe sort of see that, I mean, we're looking at a two-dimensional picture, but it would be spherical. Okay. Oh, no, it doesn't go on forever. No, the event horizon takes up a region of space. So you'd be able to go all the way around, just like you would a planet. It's just in that region, nothing can escape it.
Even if you go to the edge of the other side, you can get out.
The edge of any of the sides, you're not gonna
It's like a bubble.
Edge.
What's that?
It's like a bubble.
Kind of like a
Like
bubble.
the dirty bubble from SpongeBob. He'll eat you, but you can't get out.
Unless you have a
I don't know that reference, but we'll roll.
You are
Or pencil.
Yeah, not much.
Yeah.
You better do it.
Austin, do you have a question?
No.
Okay.
What was you tell you to pick on Alyssa?
Why would you pick on me?
Oh my gosh.
No,
Austin, you pick on everybody.
you lost your arms.
Austin's doubly interested.
Okay. Now let's talk about the effects of black holes.
Okay.
Okay?
Oh God.
Black holes have such strong gravity. Oops. Put that G with strong, we'll do another G. That they bend space and time.
Oh my gosh, it's like a Time Lord vortex.
Yes.
We're going to talk about the space part first. You can bend time. Now, all this comes from Einstein.
Did you know Einstein actually failed college?
No, he did not.
He did. He failed tests in college.
No, he didn't.
He did too.
Einstein's theory of general relativity. Oops. We're going to learn a little general relativity here. Oh, I had a basic somewhere.
You just have it for your desk.
The sticky
balls.
balls.
Alright. I want you guys to use your imagination a little bit. Actually, you know what?
Imagination.
I'm
Ken.
We can do this.
This container worries me. You ain't shut up, go crazy. You're amazing.
Okay? Jacob, grab that corner. This corner.
I mean, that where the regular
Grab
is.
that corner. Austin, come over to that.
Oh my gosh.
Uh,
Playing a game.
Okay, so,
Hold on tight, guys. Pull it, case like a parachute. Can I hold on?
please listen.
There you go. Right.
Alright.
Oh my gosh. Let's fix the problem.
Now we're going to imagine this is kind of like our idea of what space is. Now this would just be one slice of space, okay? Space would be made, because it's 3 dimensions, we would have to think of all sorts of these sheets that are kind of stacked on top of each other. This is going to be one slice of space, and we're going to put an object that has mass in it. What happens?
It bends it.
There we go.
It warps it.
It bends.
Yeah, it kind of puts a divot in it. Now, it's a fairly shallow divot, right? But the mass resting there bends the actual sheet, and it warps the space around. Listen, think about a marble rolling across here, right? If I roll a marble from here to here, when they're holding it nice and flat, it's going to follow a perfect straight line.
Right.
But what if I roll it and it goes by where the ball is? What's
Right,
that?
it's circle it and
It's
flip.
gonna curve. Now, depending on the speed, maybe it'll circle it. Maybe it's going too fast and it'll just kind of hook around and go off in this direction. But it's going to follow a different path because of that bending it down.
So it's like a train.
Can we try it? Have you ever
Person
done
on
a
a
marble?
trampoline and
Right,
a
like
ball.
a person on a trampoline, absolutely. Now, what if I put a bowling ball right here?
No, wait for
They're not
Right.
strong.
That extra mass is going to really warp it. And so there, listen, so there, if I'm going to roll my marble and keep it from getting pulled in, falling in, I'm going to have to roll it faster. Well, there's a speed limit in the universe, and that's the speed of light. Light is the fastest thing. So if we put something on here that is heavy enough and warps it enough that that fastest thing can't even escape it, that's like a black hole. Okay.
You're really good with imagination.
Thanks. So, because the strong gravity is able to bend space, it will actually change the direction of light.
What about 10?
So, even though you really can't see a black hole itself because light doesn't come from it, you can't bounce any light off of it, we can see some effects of black holes when they go in front of objects that do give off light. Now, this is a simulation, but this is what it would look like if a black hole, we saw a black hole moving in front of a galaxy. Now, this galaxy is way too far away for the black hole to pull in or anything, but it's going to change the light, change the direction of the light as it comes through.
Oh, black hole.
I wonder if the aliens live in a black hole.
It'll restart here in a minute.
You don't know that.
Okay, so here's the black hole. The light from the galaxy's way far behind it, but the light is coming towards us. But as the light goes near the black hole, it gets all bent and it changes directions. And so to us, it looks like it kind of gets, I don't know,
Glowy.
it gets what?
Glowy.
Glowy.
I think it always
Okay?
looks like an eye when it does that.
It looks like
So the light that's coming by gets warped and we get this kind of halo effect around the black hole.
Kind of looks like that eye off the Lord of the Rings.
What's about you and Lord of the Rings lately?
Look at it.
Look, it looks like an eye.
Now again, black hole is not changing the galaxy. It's not
Winding.
what's the word? It's not mutating the galaxy or pulling it around. All it's doing is changing the light as it comes through. Okay? Have you ever noticed if you have something that's kind of half in water and half out, it looks like it's like bent or broken?
Yeah.
That's because the light that goes through the water, it changes the direction. And that's what's happening right here. It looks distorted because the black hole is changing the direction of the light. Okay, so it changes the direction, or we can say it changes the path of the light. But Einstein also showed us that time is wrapped up with space. And so it has strong enough gravity that it will actually change time.
It's out like that.
Hold on, let me explain. You have a question, Emily?
How do track people always have like different last names? Like Einstein?
Stein is not as smart.
Okay.
No. That is the Hein.
One of the things that Einstein showed us that's a little bit freaky and hard to wrap your mind around is that time is relative. Okay? That means how you experience time is going to be different depending on what situation you're in. One of those situations that we're talking about today is gravity. If you went to a planet that had really strong gravity, and you were you had like some suit or something that was able to pick you up, time would go slower for you. The closer you are to a gravitational mass, the slower time goes for you. Okay? So let's say we sent Trace to this planet. Just be rid of him.
Yay!
Okay? And Trace went to that planet, and he stayed there for what seemed to him to be 1 year. And then he came back. Depending on the mass of the planet, maybe 20 years have gone by here on Earth. Okay? Now, it's not like Trace, when he's on that planet, is like all in slow motion going,
Would I be talking?
no, to him, it seems completely normal. It seems completely normal. To him, 1 year has gone by. But time is different. Because he's near that gravitational thing, time moves more slowly for him than it does for us. And so when he comes back, he's only aged 1 year. Jacob's aged 20.
Yeah.
Well,
So you
I'll
both
still have
age?
the same age.
That is true.
Technically.
What is that off?
No.
Yeah.
You will only be 1 year older.
So then I'll be 14 and have a year.
No.
Yeah.
You will be exactly as you would be as you were 14. There's no.
She sees
difference.
look on my body.
I've seen it.
Would that
I've
be in
seen
slow
it.
motion?
What's that?
I've seen it.
You
The
see
movie
what?
you're talking about.
Movie on Interstellar?
Yeah. Isn't it where that guy and then they go to a different altered universe or galaxy
Right.
and then they go to like a black hole?
They go to a planet that's very close to a black hole.
Yes.
Yeah. And so that for them, they spend only like an hour on there, but for the guy that was waiting for them up at the spaceship, yeah, like 15, 16 years have gone by.
Yeah, and when he went back to Earth, his daughter or whatever was older than him.
Right.
That one?
Yes.
Yes. So
That is Interstellar. So it's a decent movie as far as this whole time dilation and time shift thing goes. I would watch it if you get a chance.
Well, would your body development change?
No.
So then,
Again, it's Trace. There's no difference for you. You feel like a year's gone by, a normal year, nothing out of the ordinary.
Maybe that.
And for Jacob, 20 years have gone by, completely, nothing out of the ordinary. It's just that you guys don't agree on how much time has gone by because you've experienced time differently. Okay. No, there's lots of questions. Let's hit them one at a time. Ellie.
So, you went there
Uh-huh.
for a year, and it was 20 years on Earth.
Uh-huh.
Would he change, for the 20 years?
Yes.
So he would
No. It's not like Trace is going to catch up when he comes back.
No, but
Would I look
there?
like-
Is he going to be changing, through the year, into what Jacob would be in a 20
would
years?
we look like we're both 20?
1 year. Only 1 year goes by for Trace.
That's so
It
weird.
is weird. It's crazy.
So basically, if that is a live
Forever, you just go to some
that'd
planet.
be like a really
Now
long
listen, okay, here's the
It's
thing.
not the same amount of time.
Then you can come back and
No,
Right. Okay? Michael is absolutely right. It's still going to be the same amount of time for you, just compared to the people back on Earth. It's going to go. So yeah, if you want to go into the future, you just go spend some time on a planet that has a lot of gravity, and you go to the future. The problem is, there's no getting back. Can't go back.
Hey, I remember this one ride at the fair where you stand up in this one thing and it spins really fast.
Oh, yeah.
The Starship 3000. You
Okay?
can crawl all over the wall.
Yes.
you go upside
I
down and
remember
you
one
go.
day he was all over himself.
Like
Trace.
stuck in the wall.
I could tell that for walking on the ground forwards.
Sometimes what you have to add actually does make sense, but you're hitting 0% there. So that's Jacob.
Okay, so if you wore a watch or something to that other planet, would it show Earth time? Or?
No. Because time itself, it's not like your watch is just different. Time itself goes, it goes by normally for you. Okay? That's Justin.
So you wouldn't be going through, but what if you had video?
Okay. Now if you're back on Earth and you were somehow able to have a really strong telescope and see what was going on, yes, we would see Trace moving, it looked like he wasn't moving. It looked like he was moving very slowly. For Trace it would be. If you went to the planet and hung out with Trace, it would be exactly normal. But yes, from our reference frame, as normal as it can be with Trace, from our reference frame, it would look like he's moving slower. That's my
The
goal.
one that movie that you were talking about.
Yeah.
He's probably watching.
Well, he could. I mean, he didn't have a setup to be able to see him, but if he could, yes, it would look like everything was going very slowly. Okay, Casey.
Okay, so would it be backwards then if Trace had a really strong telescope and you looked
Yes.
at Earth? Would they look like they'd be like
Yes.
sprinting around? Like
Absolutely. And everything would look like it's in fast forward.
That'd be
So if you
awesome.
call him on a cell phone, you would be like,
That, I mean, sort of, but there's some distortions that happen to those waves as they go through, and actually it would change how we were able to see as well. There would have to be some things that the
So,
cameras would have to take into account, so it gets a little complex. But
what, you think 1 week for me would be like a week for them?
it just depends on the difference in gravity. Now here's the thing. We actually have to take this into account. Even though the Earth is not anything compared to a black hole, we do have a little bit of time shift here compared to something that is farther away from the Earth. It's not a huge significant difference. It's not like the astronauts that went up there came back and they're like, geez, 20 years have gone by. But it does change enough that our GPS satellites have to take it into account. Because they're so high above the ground, they experience time slightly differently than we do. Now, it's not a lot. It's like milliseconds.
They see the future.
Listen, it's milliseconds difference, but those GPS satellites only work if they have very specific times to be able to calculate where your position is. And so they actually have this all built into their calculations that their clocks have to be synchronized with ours, and because time moves more quickly for them up there, you know, if we didn't take that into account, our GPS system wouldn't work at all. Yes?
so how is Mars that far off? Or?
No. Because of course it's Mars, and then you're near a gravitational source, and that changes things. But the difference between being here and being like where time runs the fastest it ever could, again, I mean, it would take thousands of years to come up with a minute difference. And that's just because the Earth doesn't have much mass. I mean, it has a lot compared to us, but compared to things in the universe, it doesn't. I've not seen Gravity.
I've seen Gravity Falls.
I see Gravity. I like with that one chick.
And then she's the only one, and then like there's a dead guy with things like that.
This is Roark.
Yes.
Interstellar.
We should.
Seriously,
We still want us to see it.
Yeah, the problem is it's like a 3-hour movie.
But we have like 3 days next
Yeah.
class, man.
Yeah.
And you said we weren't
Yeah,
doing
man.
anything after this.
I didn't say we weren't doing anything.
But you said you were going to try, and that's you're just
Please.
You said we're taking our test on Thursday, so that means we have
Friday, Tuesday, Wednesday, and Thursday, sure.
I'll think about it.
Okay, yay!
But
We won't much of that.
all right, listen. Here's the thing. I will think about it. I will consider it. But every time you bug me about it, that's going to make me think less about it. So
Okay, let's face hold.
What are you saying? Listen.
Is there spaghetti involved with that?
Spaghettification.
Spaghettification sounds like a completely made-up word that I just threw up there, but this is, I swear, this is the technical term for what will happen to you if you were to fall into a black hole. So
You heard the spaghetti, it was like you didn't know what would happen.
No, usually
we don't know what will happen beyond the event horizon, but we know what will happen kind of up. That could be spaghetti and be falls. So,
You spaghettification.
let's say we throw Tanner into a black hole.
Oh, yeah.
It's for science.
It's for
It's for hate.
It's because we don't like you. Yes.
Okay?
Party in my house, you.
Yes. Tanner is completely for science. Okay? Here's the thing. We're going to put him in feet first. So, he's going to be falling towards the black hole. Okay, feet first. As he gets closer and closer, something strange happens.
He turns into a girl. It's hard to do.
Okay?
Sorry.
Because the gravity of the black hole is so strong, and the black hole itself is so compact, okay, the difference that Tanner feels between the gravity between the black hole and his feet and the gravity between the black hole and his head becomes significant. Okay? Right now, because my feet are closer to the ground, or closer to the earth than my head, there is a slight difference between the forces pulling it. But that difference is so small, I mean, we just ignore it. We don't worry about the fact that the earth pulls down on my head slightly less than it pulls down on my feet. Because those differences are very, very small. But as you get close to a black hole, those differences get very, very big. And that means that Tanner gets pulled into a long string of atoms. Because the gravity here is pulling so much harder than the gravity up here. And so, because you get pulled into a long string, we call it spaghettification.
So would he still be alive?
Oh no!
Oh wait.
Farted in my nose.
No, you don't survive being pulled into a line of atoms. Which doesn't happen.
You grab it.
So over time, you feel kind of the pressure, trying pulling him apart. Eventually, you get pulled apart and stretched enough that he would cease life
Just imagine how
functions.
tall you would get.
But he would get pulled, his body would get pulled until it's just a long string of atoms falling into the black hole.
Tanner finally has a beach body.
Now listen. Here's the thing. As that happens, before he passes the event horizon, as that happens and he gets pulled into this long string of particles, because of the pulling of those, he's going to actually emit light. So as Tanner goes towards the black hole, he's going to heat up into a brilliant flash of light that escapes before he falls in the black hole. Just a minute. Please put your hands up. I know there's lots of questions. I'm trying to explain it.
Amazing.
Okay? Listen. As long as that flash of light comes out before he passes the event horizon, the light can escape. So this is one of the things that scientists are looking for to find black holes, is flashes of light that are given off as material falls into the black hole. So if a black hole comes along and there's a planet that it's kind of pulling material off of, that material will actually flash brilliant light. And those are actually some of the brightest things in the universe, brighter than any stars, brighter than any supernovas. As the material gets pulled in, as it's drifting into a line of atoms. All right, Danica.
Okay, so if there's some way that you could take a spaceship and put it out there, not so close to the black hole, and you send someone out there, could you record them while they were doing this?
Getting brutally
Yes. Here's the weird thing. As they fall towards the black hole, right, you would actually start to see them less and less because the light that's coming off of them, bouncing off of Tanner, right, would actually get slowed down some. It's still able to escape, but it would get slowed down some. And when you slow down light, I don't know, there's some technical things, but basically it's pulled and stretched and it changes its color. So Tanner himself, as he falls towards the black hole, would look redder and redder and redder until the light that bounces off him would get stretched so much that it wouldn't be in the visible realm anymore, and he would disappear from our sight. He would still exist, but we wouldn't be able to see him just because the light that bounces off has been stretched.
That sounds really painful.
If you were to
Jacob had his hand up, so I'm going to answer Jacob. That's Jacob's question.
So if you were waiting to be watching him, and like you saw the flash of you, like, oh, there went Tanner.
Yes.
Cool.
Casey.
So, if the gravity is pulling on his feet more on his head, and he gets pulled into a giant string of atoms, and then gets pulled into this black hole, can the atoms redirect and make his body again what he's in the black hole?
Again, beyond the black hole, beyond the event horizon, we don't know. We think that everything kind of gets squished down into an infinite point, which doesn't really make any sense. How can you have something that is infinitely small, But I mean, the whole point is beyond the event horizon, our mathematics can't tell us anything that happens. So, I mean, there's really no, no real guesses that make any sense.
We should watch Bruce.
So, that is one area we will never understand, is the inside of the black hole. Yes, Justin.
So, it was meant to a long spin. Grab him and pull him.
Your turn.
No, you're not gonna pull them away from the black hole. Yes.
Okay, if we take you and string you into a long thing of atoms,
Uh-huh.
and put you on a scale, would you still weigh the same reason-wise?
Yeah, I mean, the atoms would,
He says.
yeah, your atoms are gonna weigh the same whether they're in your current configuration or less smaller. You're just a pile of
Reasoning.
carbon. Yes, David.
What percent of our brain is unattended?
All of it, everybody.
But
Anything else?
So we're good. A couple other things to talk about. So, one thing that people don't really quite kind of get is that, let's say we took the sun, right? And we pushed it down into its fourth travel radius and made it a black hole. Okay? Earth, other than being dark, and I mean obviously that would be bad for us, we would cool off and stuff, but as far it wouldn't get pulled into a black hole, into the black hole. Even though the black hole would be where the sun is. You have to remember, it's the same gravity basically for the Earth would keep spinning around it. You have to get within the event horizon for all this bad crap to happen. And that event horizon is going to be pretty small, it's going to be way in close to where the core of the sun would be. So if you made the sun into a black hole, as long as it kept its same mass, the Earth would keep spinning around it just the same as always. You could orbit around a black hole, no problem, as long as you're far enough away that things, you don't get pulled in. So the as far as orbits and things go, that doesn't change. It just changes what happens very close to the center of that mass.
so Mercury
Yes,
would die.
Okay,
No,
So it's kind of like,
it wouldn't change
depending
it.
on how big the black hole is,
Yes.
could Earth get close to it and then materials start getting pulled off of it?
Yeah. I mean, if a black hole came, say a rogue black hole that was just flying through space came close enough to the Earth, yeah, it would pull material in, it would pull material off of it, everything would get pulled into the black hole.
Like, even if it was like this way, it would just start getting material pulled off.
Yeah, I mean, if the event horizon was this big, air would be coming in. I mean, depending on the gravitational influence, it depends on how close it came. It could. It would have to come. I mean, one this big would have to come much closer to the Earth than one that was, say, the size of the Sun.
Oh, that was size of the sun.
Yes.
do black holes have any temperature?
Themselves, no. But the material that flashes off, like when Tanner got ripped into atomic form, that stuff would be very, it would have a high temperature as it's getting pulled in. But the black holes themselves, I mean, the whole concept of temperature kind of breaks down. Okay. All right. Now the other thing. Sometimes you hear about this in science fiction. There's this idea that a black hole could be a portal into another universe.
Teleportation is real.
Listen. Or another part of the universe. Okay? There's a couple things that kind of indicate that that's not the case. Number one, I mean, again, as you pass the event horizon, you fall into the black hole, you're going to get ripped into a stream of atoms. So even if you come out, it's going to be as a stream of atoms. That's going to do you any good.
Well, what if it does put your power down?
Please listen. The other thing is, if black holes are portals to, say, other parts of our universe, then we should see places where all that material, all that energy and material is coming out. And there's a theoretical name for those, and that's white holes. And we see no evidence for white holes, because they would be huge, really bright, glowing places in the universe where all this stuff is coming. We don't see any evidence for that. Even if it was a portal to another universe, I mean, there should be portals back, right? If there's a black hole there, we should see some white holes around here. We have never ever seen any white holes. There's no indication that those things exist. And that kind of tells us that that's probably not the case. As far as what happens to the material when it falls in the black hole, again, there's no answer to that. We have no idea. And there's no way we'll ever know because nothing can come out.
Yes.
What happens if, you know, if the black hole is just like a one-way ticket, you know, like, if you get sent to Africa, you're going to be like, you want a one-way ticket to Africa?
I was just-
Black hole. You can go in, but you can't come out. Like,
Yeah,
it will
that
take
is
you-
black
I-
hole.
no,
You
it
can go
will-
in, but you can't go
It
out.
will take you to some place, but you can't come back to some other place.
Well, again, but then, I mean, why?
That's
I mean, that would be pretty rare that that everything from this universe just ends up going to another universe, and then I mean,
That's it, the big
What if it's just the Big
No,
Bang
I'm
Theory, sending everything right back?
there's some.
Teleportation has to be real. It's in halo.
Okay, so that's black holes in a nutshell. Now we've glossed over a lot of the things. Listen, I would strongly encourage you when you get up to be like a sophomore and a junior, and you can start picking your classes a little bit more. Take astronomy. I don't know how Mr. Risford teaches it, whether he teaches about black holes or not. I always did, but I mean, if you're interested in that kind of stuff, that all has to do with astronomy, and you'll learn a lot more about it, in that class. So that's all I got.